All right, how are we doing? You can, down at the bottom of your Zoom, if you haven't checked out the reactions, on the bottom menu, you can give me a thumbs up, or you can say good in chat, or whatever you want to do if you've got that in. Or if you're not doing it, give me a thumbs up anyway.
I'm doing it.
Got a couple of thumbs ups. Got a good. I appreciate that. And I did start recording this because I can see that a few of you are missing. The important people are here. All right, so let me go over to my calculator. Okay, let me quit this. All right, so I did put this data in yesterday. So let me go to my stat in my edit. And, or maybe I didn't. Where did I put this data? I believe that's L3, isn't it? Let me open it up. It's hard to have a PowerPoint and a calculator open at the same time. So open up PowerPoint on the other computer. How many computers can you have open? All right. 3, 4, 8, 8. So this is L3. I put it in L3. And I did that because I put some other stuff in L1 and L2. So my data is in the third list. So I'm going to calculate the statistics for that list. So I'm going to go ahead and get out of here. So I'm going to do a second quit and get out of my list. Then I'm going to go back to my stat menu. And I'm going to arrow to the right, and I'm going to go to my calculate menu. And what I'm going to calculate is my one variable statistics. So far in this course, all we've talked about is one variable statistics. We're only looking at one variable here. We're only looking at how long these patients have lived after getting this antibody treatment. So we're only one variable are we looking at. So I'm going to hit enter. And now I must tell my calculator two things. I must tell my calculator where I put that data. I put it in L3. So I need to tell my calculator that the list this data is in is L3. And I do that by going second, 3. Then I need to go down to frequency, and I can just hit enter. Now, I don't have my frequencies in here because I just put all the data in a single list. So I need to delete that. So I'm just going to hit the delete key, which is up here next to my arrows, and get rid of it. Okay, now I'm going to go down to calculate and hit enter. And there are my one variable statistics. So the top number there, the X with the bar over it, is the mean of this data. So on average, the patients lived 23.6 months after receiving this antibody treatment. Now, if I go down in this list, they give me the sum of x's and the sum of the x squares because back in the old days, when we calculated standard deviation, we needed those values. But it also calculates the standard deviation for us, which is what we're going to talk about in the last section, the measure of the dispersion of our data. So S sub x and sigma, that is the Greek letter sigma sub x, are our two standard deviations. And we'll talk about this some more, but which one we use depends on whether this is a sample or a population. And this is a sample because we're looking at these patients out of the total number of patients, 8 patients. So this is a sample. So we would use S for our standard deviation instead of sigma. We'll talk about that in a little bit. Okay, the number of data points that I put in was 40. So N is 40. The minimum was 3 months. The first quartile was 15 months. I'm going to arrow down. The median, which is the other measure of our center of data that we're interested in, is 24. So the median number of months that a patient lived was 24 months, 2 years. Then it gives us the third quartile, and we're going to arrow down, and it gives us the maximum. So the minimum number of months that a patient lived was 3, the maximum was 47. So the range of our data is the 47 minus 3. Our data goes from 3 to 47. So the range is 44. All right, so now we have all the data values that we're interested in. We know that the mean, let me arrow back up. The mean is 23.575, and the median was 24. And those numbers are pretty close together, which doesn't really surprise me. I kind of would expect that those numbers would be close because of the nature of this type of data. I would expect it to have a fairly symmetric shape. And we could certainly look at the histogram of this. So we could create a histogram to look at this data and see what the shape of it is. Or we could do a stem and leaf plot to see what the shape is. So we could do that. Okay. So here in your slides in the PowerPoint in Blackboard are the instructions that I went through. Now they put their data values in L1, I put it in L3, it doesn't matter. And then how you do that calculation. All right, so here's another set of data. The following data show that the number of months patients typically wait on a transplant list before getting surgery. The data are ordered from smallest to largest. Calculate the mean and the median. And you would do exactly the same thing that you did before. You would put these data values in your calculator in a list. And then you're going to calculate the one variable statistics from that list. From that, once you calculate those, you can find the mean. In this case, it's 13.95, and the median, which is 13. And again, because of the nature of this data, I would expect it to be fairly symmetric. And symmetric meaning that the mean and the median are going to be very close to the same value. So I'll let you practice that. This PowerPoint slide is in Blackboard, Chapter 2, whatever slide number this is. I have no idea what slide number this is, but I'll let you look at that, put that data in, and check to make sure that you get the same values that we got. All right, so let's look at this example. Suppose that in a small town of 50 people, one person earns $5 million. They should be our best friend per year, and the other 49 each earn 30,000. What's the better measure of the center, the mean, or the median? So let's ponder this for a moment. We have 50 people, 49 of which are earning $30,000 a year. So if we're to calculate the mean, we can do this using the frequency. So we have 49 people earning $30,000 a year. And we have one person earning 5 million. We need to make friends out of the 50. So we can calculate the mean of this. And this is a fairly simple calculation. And I get 120, if I can put my glasses on, I can actually see what I wrote. 129,000. Now, if I were to calculate the median is the middle of this data. So if I listed off 50 of these data values, I'd have 30,000, 30,000, ... 5 million. So the middle, the median, is going to be 30,000. Now you could also put this in your calculator if you like. You could put the 30,000 in a list, and the frequency is 49. And the 5 million, and the frequency is 1. And you could calculate the median if you were so inclined, but you could do that. But the median is 30,000. So which is a better measure of the center of this data? Well, not the mean, because the mean, when you calculate the mean, it includes every single solitary data value, because that's how you calculate it. You add up all the data values and divide by the total number that you have. So it takes all those extreme values into account. So probably not the best way to measure the center of your data. The median is just in the middle. So the median has less effect by the outliers, the extreme values. So if you have extreme values, the median is probably the better measure to use. But we usually calculate the mean anyway, just so that we have it ready if we need that calculation somewhere else. But look at your data. If you have extreme values like real estate or incomes, things like that, and if you look at when the news states statistics, frequently they do state the median because they're looking at the kind of data that could have these kind of extremes. So listen next time they quote statistics on the news, what measure of central tendency they're using, either the mean or the median. Okay, the mode. Another measure of the center is the mode, and the mode is the most frequent value. And you could have more than one mode. If you have the 2 data values occurring 3 times, then you would have 2 modes. And if you have 2 modes, it's called bimodal. So let's look at this set of data. This is statistics exam scores for 20 students. And do I have a data value that occurs the most often? And it looks if I just glancing at this, it looks like the 72. Is that what it looks like to you? We got an 84 over here, but that's only 3 times. So the 72 looks to be like the data value that occurs the most, and it occurs 5 times. So the mode is 72. Now we could also calculate the mean and the median of this set of data using our calculator and see how it compares to the mode. excuse me, because we need to talk about the dispersion and the shape of data here in just a second. And comparing the mean, the median, and the mode can tell us some things about the shape of our data. So the mode, the data value that occurs most often. And you could have a data set that has no mode. If all your data values only occur once, then you have no mode. Or you could have more than one. All right, so this slide talks about finding the mean of a grouped set of data. So in this data, we have created classes, and then we determined how many students fit each class. So this is a frequency table displaying Professor Blout's last statistics test. So one student scored between 50 and 56.5, and no students scored between 56.5 and 62.5, etc. So what he did is he took his data and he ranked it, and he found the smallest score. And the smallest score, I don't know, maybe 50.5, looking at how he did this. So he did a half a score lower than his lowest score, 50.5 maybe. And then his upper score maybe was 99. So he decided he wanted however many buckets he has here, how many classes, 1, 2, 3, 4, 5, 6, 8 classes. He decided on that. And that gave him his class limits. So the first grade interval, he decided however he decided it. And then he found the frequency. Now you can't put that in a calculator. You can't put a class from the lower to the upper limit. So what we do is we find the midpoint of that class. So we take the 50 and the 56.5, and we add those together and divide by 2. And that gives us the midpoint of our class. And we do this for every class that we have listed. And that's the data that we put in our calculator. PowerPoint's not helping me. All right, so when we do that, the midpoint of our 8 classes are now in the first column. So we calculated every midpoint for every class. And then the frequency is in the second column. Now to do this on our calculator, excuse me, we put our midpoints in the first list and the frequency of that class in the second list. And now to calculate the statistics for that data, when we go to our calculate menu in our one variable statistics, we tell our calculator what our data, what list our data is in. And our data is in the first list. Now in the frequency list, we're going to tell our calculator that the frequencies of each of these data values is in the second list. So we'd go down to frequency list and we'd go second, number 2, and that would tell our calculator that the frequency is in L2. So you put the data value in L1 and your frequency in L2. And then you calculate the one variable statistics for that set of data. So on average, the class scored a 76.9. That's a good average, not bad at all. And they don't show us what the median was, but we could scroll down and figure out what the median is if we put this data in our calculator. Now he gives you the formula down there at the bottom of the slide. I wouldn't use it. I have a calculator that will do this for me. But what you do, those big sigmas, that's what this is called. This is a capital Greek letter sigma. And that means sum. You add them all up. So you add each of the data values times the frequency, just like we did before, and divide it by the total number of data values you have, which we have 19 here. And we can figure out how many data values we had by adding the second column. 1 plus 4 plus 4 plus 2 plus 3 plus 4 plus 1 is 19. So you could do it that way, but it's just as easy to put it in your calculator. Okay. Skewness. All right, so consider the data set that we have listed here. So we put this data set in our calculator and we create a histogram for it. And we can see that this distribution is perfectly symmetrical. So we have this bar right here in the middle. And on each side of that bar, we have exactly the same frequencies. So to the left and to the right, we get exactly the same frequencies from that mode. So that tallest bar is our mode. And on each side, we have the same frequencies. And if we go again to the left and to the right, to the left and to the right, we get exactly the same frequencies. So on each side of that middle bar, we have mirror images. So this data set is perfectly symmetrical around the mean and the median and the mode. So in this case, if we have symmetry, in this particular case, the mean, the median, and the mode are the same value because it's perfectly symmetrical around that tall frequency, that mode, perfectly symmetrical. Now you can have symmetrical distributions with two modes, but in this case, the mean, the median, and the mode are all going to be the same number. All the measures of central tendency will be the same number because it's perfectly symmetrical. Now, again, here's that first histogram, perfectly symmetrical. But on the second set of data, we have two modes because the two center bars are the same frequency. So that set, we're going to have two different modes, but the median would be the same value because the mean and the median are still going to be, since it's completely and totally symmetrical, are going to be the middle number. So whatever this middle number is, whatever it is, that is the mean and the median. But the mode, since I have two bars of the same frequency, I have two data values with the same frequency. Where we have 7 and 8 have the same frequency. I have two modes, which I can see from the histogram, two modes, 7 and 8. But the mean and the median would be the same value, whatever that is. What would that be? Would that be 7.5? If I looked at that correctly. Okay. Now you can have data that's skewed, and we talked about this, I think Tuesday or last Thursday. I don't know what day we talked about skewness. So if you look at this data set here, it looks like the right-hand side gets kind of chopped off. And we have this kind of tail on the left. And we call this skewed to the left. Because it's being pulled, we got this tail. It's like a wedding train on a wedding dress. It's being pulled to the left. So in this particular data set, the mean is 6.3. The median is 6.5, and the mode is 7. So you see that the median is less, the mean is less than the median, which is less than the mode. And when you have that taking place, when the mean is less than the median and the mode is greater than those two numbers, you do have left skew data. And the reason the median and the mode are higher than the median, the mean, I will spit this out. The mean is lower than the median and the mode is because you have this data here, and then you have a couple of extreme values. So The mean gets affected by every single solitary data value because that's how you calculate it. So if you have anything that's kind of extreme over here on the left, that's going to affect your mean. It's going to lower it. But the median and the mode are not affected by those extreme values because the median is the middle and the mode is just the frequency, the highest frequency, the data value that occurs most often. Now, skewed to the right, on this case, you're getting chopped off on the left. You got this tail to the right. So this is skewed to the right. And in this case, the mean is 7.7, the median is 7.5, and the mode is 7. So in this case, the mean is the largest value of the three measures of central tendency. And when that happens, you're probably going to be skewed to the right. Okay. So to summarize, generally, if the distribution of data is skewed to the left, the mean is less than the median. If you're skewed to the right, the mode is often less than the median, which is less than the mean. All right, the measures of our spread of data. Our last topic in chapter 2. And not to underemphasize this. This is really important because the standard deviation can tell you a lot about your data. And the mean is a very important measure of the center of your data, but the standard deviation can tell us if we have a process that's out of control. Because if we get a standard deviation that's really, really large, that means we're getting great variability in our data, which may be normal. But if you're manufacturing something and you're getting a great spread in your data, you've probably got a problem. So this is a very important statistics for us to calculate to look at what's happening with our data. An important characteristic of any set of data is the variation in the data. In some data sets, the data values are concentrated closely near the mean. In other data sets, the data values are more widely spread out from the mean. The most common measure of variation or spread is the standard deviation. The standard deviation is a number that measures how far the data values are from the mean. That's how it's calculated. It calculates every data value's distance from the mean and then sums them up. That's how it's calculated. So there are other measures of deviation. The range, you just take the largest and subtract the smallest data value. And that's just a quick indication of the spread of your data. Really easy to calculate. Another measure of your data is called the mid-range. Lost my notes here. And that one, you take the largest and the smallest, you add them up, and then divide that by 2. So there's two other measures of the spread of data. We do not use those. I mean, the range we use all the time. We just say, well, the range of your data is from here to here. So we use that quite a bit. The mid-range, not so often. I apparently didn't pull all my notes out. Let me see if I can find my last page of notes. Maybe not. Maybe that's it. All right. Next, the standard deviation provides a numerical measure of the overall amount of variation on a data set and can be used to determine whether a particular data value is close to or far from the mean. The standard deviation provides a measure of the overall variation in a data set. The standard deviation is always positive or 0. The standard deviation is small when the data are all concentrated close to the mean, exhibiting little variation or spread. The standard deviation is larger when the data values are more spread out from the mean, exhibiting more variation. So suppose that we are studying the amount of time customers wait in line at the checkout at a supermarket A and supermarket B. The average wait time at both supermarkets is 5 minutes. At supermarket A, the standard deviation for the wait time is 2 minutes. At supermarket B, the standard deviation for the wait time is 4 minutes. So since the standard deviation for supermarket B is larger than the standard deviation at supermarket A, you're getting more variation in the wait time. The average is the same, 2 minutes. But in supermarket B, you may be waiting anywhere from no minutes immediately walking up to a cashier and getting checked out to, who knows, 10, 15 minutes. So there's much larger variation in the wait times at the second supermarket. I don't know without seeing the actual data values what those are, but I do know that chances are in supermarket B, you're going to have a much larger variation in your wait time. I know it. That's what the standard deviation tells me. Okay, standard deviation and variance. Your concentration should not be on what the deviation, your concentration should be on what the deviation tells us about the data. Here's an example to help us understand what the standard deviation is and what it tells us about the data set. So here are the list of ages of all the close friends of Jasmine. The mean is 41.5 years old. Every friend that Jasmine has is either older or younger than the average. In other words, the ages deviate from that mean age. The question is there a number we can calculate that gives us a measure for the overall deviation of the mean? And the answer is yes, it's the standard deviation. So what you do, and you're not going to have to do this by hand, but what you do is you look at the mean is 41.5. You look at the deviation of each data value from that mean. So you look at the deviation from the mean of the 41. You look at the deviation of the 38 from the 41.5. You look at the deviation of 39 for 41.5. So you calculate all those deviations. Each data value is from the mean. And then we do a little fudging. We square them because we want to assure that it's positive. And then we add them all up. And then we divide by the number of data values we have. That's what your calculator is doing. It's calculating the deviations each of your data values is from your mean. So here are the formulas for this. And aren't you glad that you don't have to do this? We used to, when we did this by hand, we set it up in tables to help us do these calculations. You don't have to do these calculations by hand. So which calculation you use depends on whether or not your data is a population or a sample. So what you do to find the sample standard deviation, that's what the S represents, sample. So if your data set is a sample of a population, again, you take each one of your data values and you subtract from it the average. That's this right here. Then you take that number and you square it. And we square it to assure that it's positive. Then we divide that by the size of our sample minus 1. So if we do the standard deviation of a sample, the denominator is n minus 1. We do that calculation, and then we take the square root of it. So we kind of fudge it. We square it, then we take the square root of it to make sure that it's positive. Who thought this up? Isn't this clever? It's very clever. Now, if it's a population, and there is a difference, so when you're doing your homework problems, make sure you know which one you're looking at. Is your data a sample of the population, or is it a population? It makes a difference. So if it's a population, we use the Greek letter sigma. That is the lowercase sigma. Okay, and in this case, you do the same thing. You take each of your data values and you subtract from it, and now we have another Greek letter. How many Greek letters can you have? We have this Greek letter here, which is mu, And mu represents a population mean. So if you know your data is a population, the mean is represented by the Greek letter mu. So you take each of your data values and you subtract this mean, you sum them up, square them, sum them up, divide this, in this case, by the number of data values you have. So capital N is the number in your population. And then you take square root of it. So they are calculated differently. So when you do this in your calculator and you see the sigma sub x and the s sub x, they are going to be different numbers because they are calculated slightly different. To calculate the sample standard deviation, you divide by the sample size minus 1. When you calculate the population standard deviation, you divide by the number in your population. Slightly different calculation, slightly different results. So, like I said, be sure to read your problems carefully and determine whether or not the data that you have in your problem is a population or a sample, because it does make a difference in what value you want to input in MyOpenMath. Now, the variance, you just take the standard deviation and you square it. That's the only difference between the standard deviation and the variance. All right, so let's see if we can't calculate a standard deviation and a variance. So here is Jasmine's friends again. If she has thousands of social media friends, which is very possible with all the different social media platforms anymore, Twitter, TikTok, Facebook, all those social media platforms, Instagram, you could easily, just being a normal human being, have thousands of followers. And the list of ages were a sample of her friends. What would we have to? We would have to slightly modify our calculation of the variance and standard deviation. And again, since you're going to let your calculator do this, the value you're going to look at, if this is a sample, you're going to look for S sub x. If it's a population, you're going to look at sigma sub x. Okay, so I'm not going to put this in. We're just going to look at this. Because anytime you put a set of data in your calculator and you calculate it for one variable statistics, it will calculate both the population and sample standard deviation for you. So given her set of friends, and this is a sample of the total number of friends she has in social media, find the population and sample variance and standard deviation and of Jasmine's friends. So we would put this data in a list. We're getting fairly practiced at that. So again, you're going to go stat on your calculator. Whoops. So find your stat button. And the first item is the edit menu. And that will get you to your lists. So pick a list that you want to put this data in. And then calculate the one variable statistics. So once you have it in your list, you exit out of that list. So you do a second quit. And then you go back in to stat. You arrow over to your calculate menu. And you calculate the one variable statistics. Okay, and so what we see here from this list is that the sample standard deviation was, I can't see that without glasses, put glasses on. The sample standard deviation was 3.1, and the population standard deviation was 3, rounded off to the whole number. So again, I should expect that the population standard deviation is smaller because you're dividing by a bigger number, and that's what happens when you divide by a larger number than a smaller number, the result will be smaller. So we would expect the population standard deviation to be a smaller number than the sample standard deviation. Now, they did do something here. They squared this to find the variance, which we probably should talk about. Get out of here. Okay, I can square any variable that I have stored. And since it just calculated my one variable statistics, all those numbers are stored in your calculator. So if I go to my variables and I go down to number 5, do you see number 5 down there? That's my statistics variables. So I went variables, which is right below my arrows. And we are going to come back to that menu again. So right below my arrows, just to the left of my clear button is my variables button. And I'm going to look at my statistics variables, which is number 5. And there are all the variables that my calculator just calculated for me. So if I want to find the variance, the sample variance, I'm going to square number 3. So I'm going to go number 3, and then just hit my square button over here on the left, right there. And that will give me the sample variance of the data that we used earlier. And to calculate my my population variance, I can spit it out. I again go to my variables menu. Number 5 is statistics. Number 4 is my population standard deviation, sigma sub x. And I can square that using my square button. So there is my population variance. So the difference between the standard deviation and the variance is that the variance is the square of your standard deviation. So S sub x is your sample standard deviation. Sigma sub x is your population standard deviation. And to find the variance, we square those values. And again, we would expect the population standard deviation, population variance to be smaller than the sample standard deviation, sample variance, because of the way we calculate those. So population standard deviation will be smaller. All right. All right, so one of the things we use standard deviation for is to determine if we have extreme values. Now, in the previous sections, we looked at the interquartile range. So we took Q3 and we subtracted Q1. And we multiplied that by 1.5. And then we looked at, do I have any values that are smaller than the first quartile by that amount? Or do I have any values that are larger than that? And we said those could be outliers. Well, we can use the standard deviation similarly. A rule of thumb is if you have a data value that's smaller than your mean by 2 standard deviations, that might be an extreme value. It might be an outlier. Or if you have a data value that's above your mean by 2 standard deviations, that could be an extreme value or an outlier. So the rule of thumb is it's not a rigid. We're going to talk about this later when we talk about the normal distribution, but typically 98% of our values should be within plus or minus 2 standard deviations of the mean. So if you have any values that are larger than 2 standard deviations from the mean or smaller than the mean by 2 standard deviations, they're outside of what we might consider normal. So if we look at Jasmine's data, we found the standard deviation from that data. We could look at what's 2 standard deviations below the mean of that data and what's 2 standard deviations above the mean of that data, and to see if she has any friends that are outside that range. All her friends are within 2 standard deviations of the mean, whatever that means. She doesn't have a large variation in the ages of her friends from the mean. Okay, so now we're going to actually calculate this. So I'm going to give you a minute if you want to put that data in your calculator. This is first exam scores from a spring pre-calculus class. So if you want to put that data in your calculator, we're going to calculate the mean, the standard deviation, the median, the quartiles, the interquartile range, and then we're going to do a box plot and a histogram of this on the same axes. So I'm going to show you how to do that. So I'm going to give you a minute or two to do that, put that data in a list, and then I'll come back. When you get done, if you can give me a thumbs up or a good in chat, whatever you want to do. A thumbs up. Second thumbs up. Thank you. I am recording this today, and I recorded Tuesdays also, and those are in YouTube. I just haven't posted the links yet, so I'll do that later today. I'll get those links posted. I'll post them in an announcement so you can watch those videos if you're so inclined to do so. Okay, I got about 3 thumbs up. Right, so the first part of this problem, they say create a chart containing the data, frequencies, relative frequencies, and cumulative relative frequencies to 2 decimal places. So this we would do by hand. The second part of this, all of this, we can use the calculator for. Now, that's not to say we're not going to use the calculator to calculate the frequencies because we are the relative frequencies because we are. That's just too hard of a calculation to do in your head. So we're going to set up a chart, set up a table, and we'll do those calculations using our calculator. So we have data values from 33 to 100. The 33 occurs once, the 42 occurs once, the 49 twice. So there are our frequencies. So we have here a table that we've created. The first column is the data values, 33 to 100. The second column is the frequency that that data value occurs. Now we had, how many students here? Did I count? Did they tell me? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. 31 data values. So to find the relative frequency, which is the third column, we take the frequency and divide it by the number of data values we have. So 0.032 is 1 divided by 31. So it's the frequency divided by the total number of data values you have. So the 42, its relative frequency is also 1 over 31, or 0.032. Now 49 occurs twice, so its relative frequency would be 2 over 31. Now to get the cumulative frequency, we add the frequencies together. So the cumulative frequency of 42 is the sum of the two frequencies, 0.032 and 0.032. And so the cumulative frequency of 49 is 0.129, etc. Now at the bottom, we should get 100 or 1. We should get 1 down here. And we don't because of round off error. And that's one of the things that you have to be really, really careful with when you're dealing with statistics is round off error. Now, we could have carried those cumulative frequencies out to 4 or 5 decimal places, and then when we sum them up, get 1. And you're going to find this in a later chapter in my open math where this becomes an issue. And we'll talk about that when it occurs, that when you're rounding off and then you're summing up at the bottom, you can get round off error. In my math, my open math, I'll count it wrong, even though you've used the rounded off figures. So when that happens, you're going to tell me and I'm going to give you credit for it. Because it's like 1 decimal place off and it'll count it wrong. Stupid, but it does. But that's the reason it's not adding up to ones, because we've rounded off. And in statistics, engineering, mathematics, you should carry as many decimal places as you can through all your calculations and then round off at the bitter end. That's when you round off. All right, so now we've put this data in our calculator. So I am going to go over to my calculator. And I'm going to see where I put that data. And I believe I put that, where did I put that? Do I not have it in my calculator? Oh, surely I put this in my calculator. I thought I did. Bummer. Ugh. I'm feeling really stupid right now. I swore I put this in my calculator. I must have overwritten it last night. Give me a second here. like watching paint dry. I could have sworn I put this in my calculator. I was kind of out of it last night, so who knows what I did. How long can I use COVID as an excuse? Okay. Well, I'm going to have to use L5. I'm doing it backwards. Oh, Lisa, stop doing that. Oh, I did it again. All right. So we got 1. If I get any of these wrong, you just forgive me. I think I already got one wrong. I think that's 1. You're going to have to forgive me if I got these wrong. Where are we? 68 is 2. 69 is 2. 72 is 1. 73 is 1. 74 is 1. 78. That's why I try to get them in early so I don't make mistakes. 83 was 1. 88 was 3. 90 was 1. 92 was 1. 94 was 4. 96 was 1. And 100 was 1. All right. Let me get out of here. So now I'm going to calculate my one variable statistics. So I'm going to calculate one variable statistics, and I went backwards. So my list is L6. So that's second 6. And my frequency was L5. So second L5. And let's calculate. How close did I get to being right? Oh, I think I actually might have got that right. All right, so I got the average to be 73 point, I got it wrong, 73.125. That's because I typed something in wrong. The correct average is 73.516. So let me go back to my PowerPoint slide. So the average is 73.516, and the standard deviation of the sample is 17.92. The first quartile is 61, the median is 73, and the third quartile is 90. The range is, the interquartile range is 90 minus 61. The difference in Q3 and Q1, okay? So now we have all those statistics. Now we can do a histogram and a box plot on the same graph. So the way you do this is we're going to go to our stat plots, and we're going to graph our stat plots based on this data, but we're going to do it in the same graph. So I'm going to do second stat plot, and I'm going to turn on plot number 1, and it is on. And I'm going to first, on plot number 1, draw my box plot. Now my box plot is going to be, my list was L6, and my frequency was L5. And then once I have that done, do you see at the top here where I have plot 1, plot 2? I'm going to go back up there and I'm going to go to plot 2 and I'm going to turn that on. So by hitting enter, and then I'm going to hit enter again and turn it on, and I'm going to plot a histogram. Oops, too far. So the first plot was a box plot. The second plot is a histogram. So I'm going to do the same thing. And my list was in L6 because I was backwards. And my frequency was in L5. And to get this to look the way that I want it to look, I need to decide how many bars I want. And I need to decide, then I need to calculate the scale I'm going to use for X, okay? So I'm going to get out of here and I'm going to go to window. Now, my minimum value, the minimum data value I have is 33. So I'm going to want my window to go from 32.5 to 100.5. I know I'm out of time. Just give me a second. Okay, and I wanted 5 bars. So I'm going to do my scale to be 100. It should be 100.5. I want my scale to be 100.5 minus 32.5 divided by 5 because I want 5 bars. So I'm going to use my parentheses. And I'm going to do 100.5 minus 32.5. Close my parentheses and divide by 5 because I wanted 5 bars. And it should calculate the scale for me. Okay, and then it defaults to a Y value, and we can use that default. They actually say to go from negative 2.4 to 17, so I'll do that. Because I think we certainly didn't have a Y max of 17, but we do want to see both charts on the same graph. And once I get that set up, I can just hit graph. And so you can see on this graph now, my box plot, how it compares to my histogram. All right, get back to Zoom. All right, so are there any questions? I've kept you 2 minutes over. I apologize for that. Are there any questions on this? Now, the one thing we didn't do, which we'll look at on Tuesday because I ran out of time, is z-scores. It's a very simple calculation and you can compare to standard deviations using that z-score. I'm not sure you have any questions on it, but your homework's not due till Tuesday, I think. So I have time to do a quick review of that on Tuesday before your homework's due. Are there any questions? Well, thank you very much for staying 2 minutes after, and I apologize for keeping you after. We'll see you Tuesday.
Bye, ma'am.
Bye.
Yes, ma'am.